Swayam Prabha. Digital India. Educated India.
Now thankfully our reference is VAC, so I can simply write VAC as Vm sin omega t. Our reference is VAC, so I can simply write this as Vm sin omega t d omega t. Now the entire thing has to be averaged over 2 pi by 3. 2 pi by 3, not 2 pi, 2 pi by 3. Because this will repeat again. I will have 6 and 1, 1 and 2. And after that, I am going to have 2 and 3 for a short while, then 3 and 4 for a longer duration, and so on and so forth. So we will have different kinds of outputs whenever I have different firing angles. We will look at one more firing angle at least, and then we will decide exactly how the output changes. So in this case, if I try to look at the supply current, maybe I have a huge inductive load, RL load, and the current is ripple free. Let me assume the current is ripple free. It is a straight current. So if I try to draw the DC current, maybe I am going to have a DC current like this. So this is the DC current. So if my DC current is somewhat like this, I had to see what happens on the AC side. How the AC side currents are changing. So please look at this circuit. So if I have if 1 is conducting, device number 1 is conducting, A phase current is positive. If device number 4 is conducting, A phase current is going to be negative. Right? So I have to look for wherever 1 is conducting, I will have correspondingly that particular current to be, A phase current to be positive. So let me take a look at this. I am going to have here device number 1 is conducting. So I am going to have clearly A phase current coming up as positive until here. This is A phase current, and please note it is for 120 degrees, no doubt. This is A phase current whenever 1 is conducting. And if I try to look at the other side of the current, wherever 4 is conducting. So this is going to be 4, whereas this is going to be 1. And in between I have only 30 degrees, not 60 degrees. In the other fully controlled converter, because we had symmetrical conduction of each of the positive and negative devices, I had 120 degree current in the positive, 60 degree of zero current interval, again 120 degrees current in the negative, again 60 degrees of zero current interval. So it was separated very nicely by 60 degree or symmetrically. Whereas here if I try to look at, for this entire duration, 6 is going to conduct from here to here. So I am going to have zero current here, this is zero current, until I am going to have 1 coming up along with 6. So this is all zero current. So the zero current interval will continue for almost 90 degrees once the negative half cycle of the current is over. Because as we said, 3 and 4 conduct for some time, and after that I am going to have 4 and 5 conducting for probably a longer duration, or 5 and 6 conducting for a longer duration, 90 degrees duration. So that is going to essentially make A phase completely not having any current. So similarly, if I try to look at, for example, B phase current, right? B phase current is going to be somewhat like this. I am going to have B phase current positive here whenever 3 is conducting. Right? So this is IA, this is IB, right? And 6, whenever 6 is conducting, so 6 is conducting here. So I'm going to have 6 conducting here, and this interval is only 30 degrees, right? But 6 is probably going to conduct again here, and this interval will be 90 degrees, right? So I am going to have the positive current duration for 120 degrees and negative current duration for 120 degrees, but they are not separated symmetrically from each other. On one side they are separated by 30 degrees, on the other side they are separated by 90 degrees, right? So if I try to find out what is the RMS current, if I say this is ID, per phase RMS current if I try to calculate, right? It conducts basically for 240 degrees, inclusive of positive and negative, right? And it doesn't conduct for 120 degrees. So it conducts for 2/3 of the duration, and it doesn't conduct for 1/3 of the duration. So I have to essentially say, I have to probably integrate it from about, if I say this is 0 and this is 2 pi by 3, for example, so I should say 0 to 2 pi by 3, right? ID square d omega t, and I have to divide this by pi, because I'm talking about half a cycle, RMS current. I'm trying to calculate the RMS current. Positive and negative halves are exactly symmetrical, so it is sufficient if I do it only for half a cycle, right? And I have to take a square root, that's it. So this will come out to be ID into root of 2 by 3, right? So root of 2 by 3 times ID, yes. Yeah, so I could have done that, and then I could have divided this by 2 pi. Rather than that, I have taken only half the cycle. I could have done this as ID square from 0 to 2 pi by 3, another ID square from, say, 2 pi, if this is 2 pi by 3, this is 150 degrees, whatever it is, 150 to 270. I could have taken it like that, but rather than that, if I just integrate for half the cycle, that's more than sufficient, because they are symmetrical. No, no. When you have purely resistive load, you just cannot make this approximation. So for purely resistive loads, it is not easy to calculate the current unless you are given exact numerical values. If you are given exact numerical values, you will be able to calculate by integrating and substituting the actual DC values and so on and so forth. Otherwise you cannot. But this is basically for the case where there is a large amount of inductance, highly lagging load, right? Let us now try to take this is true even for a 3-phase fully controlled converter. I'm sure you realize that, because if I am going to have, 120 degree current in the positive half cycle and 120 degree current in the negative half cycle, and in between 60 degrees division, it doesn't matter whether it is 60 degree or 30 degree, I'm going to get the RMS value like this. So this is going to be IA RMS or IB RMS or IC RMS, irrespective of whether it is single phase or 3-phase fully controlled converter. But 3-phase semi-controlled or fully controlled converter. But 3-phase semi-controlled converter, when we go for a little larger values of firing angles, they are going to behave a little differently. Let us try to take a look at that. Okay. So let me probably take again 3-phase waveforms. So these are the 3 phases. This is A, this is B, and this is C. Let's take maybe not 60, maybe, shall we go 90 or a little more than 90, maybe. So let us say we'll go for 90 degrees. Let me check for alpha equal to 90 degrees what happens. Let me take it for alpha equal to 90. So which means This is actually my alpha equal to 0. So I'm going to have this is alpha equal to 90. Am I right? So this will be where T1 will be fired. This is where T2 will be fired. This is where T3 will be fired. Right? T3 and T5. Right? This is for the case of alpha equal to 90. Now if I try to look at it, again, I am going to have clearly for this duration, I will have 6 conducting. There is no opportunity for 1 to come in touch with, 6 at all, because 1 is actually being fired here. So 1 and 6 are not getting in touch with each other at all, because when you have fired 1, 6 has already ceased to be the most negative device. So 6 will never join hands with 1. So what I will have is, here I am going to have, for this duration, it is 1 and 2. And for this duration, I am going to have from here to here, it is going to be 4. Right? So I am going to have actually 1 and 2 conducting for this duration. From here it is going to start and it will conduct until here. 1 and 2 will conduct for this duration automatically. After that, what happens? When 1 and 2 are conducting, it is VAC. We are very sure of that. That's not a problem. After that, what happens is, here 1 and 4 conduct. And 1 and 4 are in the same leg. They are not in 2 different legs. So it will freewheel. Obviously, freewheeling will take place when I have 2 devices which are in the same leg conducting simultaneously. Right? So semi-controlled converter will get into freewheeling the moment you have the 2 devices together conducting in the same leg, because one of them is diodes. You don't have a control over preventing its conduction. Right? So I'm going to have actually, if I try to draw the waveform, for this I have to draw 1 and 2, and please note this is 0 crossing of VAC. Here A and C are crossing with each other. So because of which it is 0. VAC will be 0 at this point. Right? And it is starting to conduct here. And how much is the duration? This is 60 degrees and this is 30 degrees. So totally 90 degrees I am getting 1 and 2 conducting. So that means it should start from the peak and come down to 0. So I should have essentially this as VAC part of the sinusoid. So it is starting from the peak and ending up in 0. And when it is freewheeling, I am going to have 0 voltage clearly. And after that I am going to have 3 and 4 conducting. When 3 and 4 are conducting, it is VBA. So I am going to have again VBA. Right? And then after that it is going to be 0, because if I say that 4 is conducting until here and 3 is continuing until this point. So 6 has already started. So there will be 0. 3 and 6 will conduct for some time. Right? And after that I am going to have 5 and 6 conducting. If 5 and 6 are conducting, I am going to have VCB. Right? So I am getting all sorts of different varieties of waveform when I am looking at semi-controlled converter. But actually if you try to derive the expression for each of the cases, you would see that it will be 3Vm by 2 pi into 1 plus cos alpha. This is what you will get irrespective of whatever is your alpha. This will be the VDC average for semi-converter. No. It will probably come from here itself because you would have fired T1 here. So you would have had 1 and 2 continuously conducting for the entire 120 degrees. If I had fired, if I say alpha is equal to 60, for that I would have fired T1 here. So I would have had 1 and 2 continuously for 120 degrees. I will never have zero current interval. Okay? Zero voltage interval. Then I will have T3 actually fired here. T3 will be fired here. So I will have 3 and 4. But what I will get as the waveform will be something like this. It will go like this and then it will come down. So this will be VAC. This is for alpha equal to 60. Because I have fired it 30 degrees ahead. So there is no question of short circuiting by 2 devices. Right? So this is VAC and then you will have again VBA and similarly you will have something like this and then coming like this. So this is going to be VCB. Right? One major thing here will be, please note, in alpha equal to 60 degree case, I will have 1 conducting here, because of which I will have a positive current here. And A conducting here, that is 4, so there will be a negative current here. Please note, there is no gap at all between the positive and negative current. Right? And 120 degrees it is dead. This is for alpha equal to 60. So for this 120 degrees, it will be zero current. Completely. Right? Whereas here, whenever there is freewheeling, the supply is completely eliminated or isolated. The supply is not going to care about what happens to the load, because only between the load and the freewheeling leg there will be current. So if I am having, for example, these two are freewheeling, I am going to have simply the current going like this. Right? There is nothing that is going through the supply. It is just going round and round in this. That's it. So the supply will be deprived of any current, or it will not carry any current during the freewheeling. So if I try to look at the current here in this particular case, I would see that, for example, during VAC I will have a positive current, no doubt. I will have zero current during this time and I will have a negative current during this time. This will be IA. Get my point? So I am going to get positive current for only 90 degrees here. Negative current again only for 90 degrees. So 90 plus 90, 180 ho gaya. Rest of 180 it will be dead. No current at all. So in this case that root of 2 by 3 will not work. So semi-converter is a pain basically for analysis. It's not very easy to analyze semi-converter in general. It's going to be pretty difficult unless you are given clearly the firing angle and clearly what kind of load and so on and so forth. It becomes kind of difficult, but one major advantage of the semi-converter is, of course, if I compare with fully controlled converter, which is 3 Vm by pi cos alpha. This is the expression for fully controlled converter. I am sure from these two you can realize that I will get more value for, in this particular case. I hope I have written this expression correctly. maybe verify it. Vm by pi into 1 plus cos alpha is for single phase. Yes, it is the same. 3 Vm by 2 pi into 1 plus cos alpha is the case corresponding to the semi-controlled converter, and 3 Vm by pi cos alpha is the fully controlled converter. Clearly, semi-controlled converter for a given alpha other than 0 will yield a higher value of voltage. If I, for example, take alpha equal to 90 degrees, here it is 0. Whereas if I take alpha equal to 90 degrees, in the other case it will be 3 Vm by 2 pi. So, if I try to actually plot what is the value of voltage I get with respect to alpha, right? So, if I say that if this is my alpha and this is the VDC, right? I will have the VDC, basically VDC average, I will be getting a higher value for the semi-controlled converter, whereas for the fully controlled converter, I will get much lower value because of the fact that I have 1 plus cos alpha expression in my semi-controlled converter, whereas I have only alpha expression for the fully controlled converter, right? At alpha equal to 0 degrees, both of them will have the same value. At alpha equal to 0 degrees, both of them will have the same value. But as I see the fully controlled converter, I am going to see that it probably goes like this and then it goes into the negative direction. What do you mean by negative direction? We are yet to discuss, which we are slowly migrating to. Okay? So, the voltage will go into negative direction if I go for, this is alpha equal to 90 degrees, if I say. Whereas, if I am talking about a semi-controlled converter, it will still be positive even until alpha equal to 180, at alpha equal to 180 degrees only it will become 0. Right? It cannot become really 0 before that. So, I am going to have essentially this becoming 0 only at 180 degrees. If I may say that this is where it is 180 degrees. You will not be able to have the line commutation at all. It will not go off. I don't know whether you guys have understood that, because we have repeatedly said in the single phase case also, when a new device comes in, the old device is actually reverse biasing the, old device is getting reverse biased by the new device. Right? That is the reason why it is going off. So, alpha equal to 180 is theoretical limit. Practically, I might have to do it a little ahead of time. What I mean is, if I have a fully controlled converter, let me probably talk about commutation again. So, these are the 6 devices. So, if I am having T1 fired and T5 is going off, let us say I am firing T1, okay? When I am firing T1, this is A, this is B, this is C, this happens to be a short circuit. Already this is conducting, right? So, whatever is this C, that C comes here. I am going by the same logic, whatever we talked earlier. So, for me to fire T1, VAC has to be positive. If VAC is not positive, I will not be able to fire T1. And VAC 0 crossing is alpha equal to 0. So, obviously at alpha equal to 180, VAC will start going in the reverse direction. So, I will not be able to fire T1 if I want to fire it after alpha equal to 180 degrees. So, alpha equal to 180 degrees is the theoretical limit for firing any device, because after that it is going to get reverse biased. I am looking at basically the previous device which is conducting, that is bringing in some line voltage. And the new device which is going to get in, it is going to have a phase voltage on the other side. So the line voltage which is coming across the device has to be positive. If that is not positive, there is no way you can fire that particular device. So alpha equal to 180 degree is the theoretical limit that we generally set for, making sure that the device gets into conduction. But this is assuming that the forward voltage drop is 0. If the forward voltage drop happens to be 2 volts, 3 volts, then I can't go until 180 degrees. I have to push it a little ahead, maybe 179, 176 degrees, because I need at least that much of voltage across the device so that it is having some forward biasing voltage across it, right? This is one thing. Second thing is, the moment this gets into conduction, this becomes a short circuit. So now this A will come here. Once A comes here, we have to see whether VAC is able to reverse bias the outgoing device. The outgoing device has at least some turn off time. It may have 50 microsecond, 100 microsecond, 120 microsecond, whatever. So for that duration, I have to make sure that it is reverse biased and recombination takes place. So that is also true only if alpha is until 180. Because if alpha is beyond 180, VAC we said will be negative. If VAC is negative, I'm going to forward bias 5, device number 5. So there is no way device number 5 will get recombined or it will not turn off. So normally I am not going to be able to operate any of these converters beyond alpha equal to 180 degrees. We will be able to operate it from alpha equal to 0 until alpha equal to 180 degrees. That is the limit. Beyond that we will not be able to operate it unless maybe we have some other commutation circuit, some other thing which we are not discussing, that is not under the purview of this course. So we are only talking about natural commutation or line commutation, where the supply voltages which are going from positive half cycle to negative half cycle automatically turn off the device. Right? Now let us try to see what it means to be alpha greater than 90, because I told you that there is a negative voltage that is coming up, but we said AC to DC conversion. DC means unidirectional and we are talking about negative voltage. Doesn't make much sense. So we have to first of all understand what we mean by the negative voltage, where is it applied, how is it going to be useful in any of the applications, right? So let us say fully controlled converter with